Hello friends, welcome back to this online lecture series on earthquake resistant design of structures. In the previous lecture, we have been discussing regarding the several codal provisions laid down by AS 1893 in 2016, that is the criteria for earthquake resistant design of structures, that is particularly about the buildings, right? Now, from today onwards, we are going to start our discussion or focus our discussion on a couple of numericals, that is the part of this course curriculum. And that is why we are going to start our discussion today with the concept of center of mass and center of stiffness. And once we understand the concept of center of mass and center of stiffness, then we will start with the numericals for center of mass as well as center of stiffness. Right now, as we have discussed in the lecture series ahead, and I hope that everybody might be remembering this also, that the concept of center of mass and center of stiffness is very important. For example, when we took the example of the rope swing, therein we discussed that for the better functionality of the rope swing, it was important that the center of mass and the CG of the system should coincide with each other. And same thing will be applicable in case of buildings also. That is, the CG of the building and the center of mass and the center of stiffness should coincide so that the torsion in the building will not be there. However, if there is a difference in either of these centers, and as a result of that, the eccentricity will be generated, which will be known as the static eccentricity. And due to generation of the static eccentricity, the torsion is likely to be there in plan. Right. So let us start our discussion today with first understanding the definition of center of mass. Now, here I am going to discuss the definition in two parts. First is going to be the general definition, where we talk about the system or a mass or an object, and secondly we focus on the part of the building. Right. So if I talk about in general the center of mass of a system, then it can be defined as the center of mass of a system is a specific point where it seems that the entire mass of the system is likely to be concentrated, right? That is, it is going to be one particular point where the entire mass of the system is likely to be concentrated. And if in other words, if I talk, then I can also say that center of mass is going to be the point from wherein there is going to be equal distribution of mass in all the directions, irrespective of the gravitational field, right? From that particular onwards, that particular point onwards, the distribution of mass is going to be equal in all the directions, and the gravitational field will not be having any role in that particular case, right? And if we talk in terms of object, then in that case it is going to be restricted. For example, if I talk about the rigid body, that is, in case of a rigid body, the position of its center of mass is fixed in relation to the object, right? So let us see a couple of examples to better understand this concept. Right now, center of mass is going to be there in both the cases, that is symmetrical objects also, asymmetrical objects also, or symmetric geometries and objects with unsymmetric geometries also. So here I have taken the examples of both the cases, where in the top figure you can see the examples of the geometrical shapes that are there, that is cylinder, triangle, circle, square, rectangle, right? And on the bottom side we have the unsymmetrical shape or the asymmetrical shapes that you can see over here. So when I am talking about the symmetrical shapes, then in that case the possibility of finding out the center of mass is going to be relatively easy. Why? Because in most of the cases we anticipate that the center of mass and the center of CG of the system, that is the center of gravity of the system, will coincide with each other, right? So if I talk about the symmetric systems, then you can see that the CG or the point of CG of the point that is highlighted in blue is indicating the center of mass also, and it is indicating the center of gravity also in that particular case. So if I talk about the triangle, then in case of triangle I can see that it is going to be at certain distance from the base. Similarly for the circle, for the square also it is shown that it is going to be at the center itself from both the direction, that is x direction also as well as y direction also. But the problem is going to start when it is going to be having an asymmetric geometry. So when it is going to have an asymmetric geometry, then in that case you will need to do certain amount of calculations, and based on that calculations you will be able to find out the center of mass and center of gravity and center of stiffness of that particular system, right? However, it is important to find in both the cases, whether it is symmetric cases or unsymmetric cases. In both the cases, center of mass is going to be there. Why? Because what is going to happen is that the floor plan may be symmetric in nature, it may be asymmetric in nature also, and that is why we discuss the concept of vertical irregularities also, and that also we try to focus that whenever the irregular geometry is shaped there, then in that case it should be converted into regular geometry. And if you convert into regular geometry, then in that case the possibility of having the torsion in the plan can be averted. And one of the reasons is going to be this, because if you are going to have irregular geometry, then as a result of that the CG, there will be difference in the center of mass and center of stiffness, and as a result of that the change is likely to be there, right? So coming to the point of center of mass in buildings, that is, the center of mass is the point wherein the floor of, that is mass of the entire floor is going to be act. And if I talk about the center of stiffness or center of rigidity, then I can say that it is going to be the point where the center of, or you can see the entire stiffness of the building is going to act. That is, center of mass is the point where the mass of the entire floor is going to act, and center of rigidity is the point where the stiffness of entire building is going to be acting, right? So this is the difference between center of mass and center of rigidity or center of stiffness, right? So when you talk about mass in case of buildings, then in case of mass, the mass is majorly contributed by the weight of beam and slabs. And if you talk about stiffness, then we know that stiffness is majorly going to be contributed by the vertical elements, that is the columns and the shear walls that are going to be present in the building, right? So when you do the three-dimensional modeling of a particular structure in case of U-tabs or stab, then in that case, after modeling, we study the behavior, that is, we study the translation in x direction, we study the translation in z direction. And when you do that particular thing, then as we have discussed in the earlier lectures, you may observe that sometimes the twisting is taking place about the horizontal axis, or it may, in most of the cases, it is going to take place about the vertical axis. Now, this twisting that is going to take place about the vertical axis is going to be contributed or attributed to this difference in center of mass and center of stiffness that is going to be there. If both of them are matching, then as a result of that, the torsion will not be there in the building. And if torsion is averted, then the performance of the building is going to be greatly advantageous. However, if torsion is present, then as we have discussed in the earlier lecture series and as some of the suggestions are given in IS standard also, these changes, some of the changes are indicated, these changes can be applied, and as a result of that, attempt should be made to remove the torsion from the building, right? So this is the importance of center of mass and center of stiffness for good performance of the building in long term when subjected to lateral loads, right? So now based on this concept, let us try and look at couple of examples. Now first example is the example where we are going to try and find out the center of mass of a particular building, right? So as you can see in the figure, a floor plan is given where the dimension is 30 meters by 14 meters, right? And the distribution of floor mass, that is the mass on the floor, is going to be different. That is, on the first side you can see that 1400 kg per meter square the intensity is given, then 1200 kg per meter square the intensity is given, and then 1000 kg per meter square the intensity is given, right? So 30 meter is the dimension x direction, 14 meter is the dimension in y direction, and the question that is asked is find out the center of mass of this particular system or floor, right? So what we do is that first of all we need to decide a point of origin, right? So as what I have done is that starting from the left hand side bottom corner, I have given the name as A, B, C and D, right? And accordingly I have selected the left bottom corner, that is the point A, as the point of origin, which I can also say as 0, 0 point, right? So whatever distances I will be calculating will be with respect to this point of origin, that is 0, 0, right? So whatever point of origin you select, based on that the distance has to be calculated, right? So here I am calculating I am considering the left hand side bottommost portion, that is point A, as the point where which is going to be my point of origin, right? Now second thing what is happening is that if you look at the distribution of mass that is shown, then the 1400 kg per meter square area is forming a symmetric area. Then 1200 kg per meter square is also forming a symmetric area, that is, it is having a rectangular shape. So there the calculation is going to be easy. However, for the third part, which is going to be forming the major part of the floor, that is 1000 kg per meter square, there you have the unsymmetric shape. So what I have done, or what the first step that we have to do is that we have to convert the unsymmetric shape into symmetrical shape, and that is why what I have done is I have extended the line from the first part, that is a dotted line is shown in the vertical direction, and as a result of that the entire floor can be divided into 4 parts. That is, the first part is going to have 1400 kg per meter square, second part is going to have 1000 kg per meter square, third part is also going to have 1000 kg per meter square, and fourth part is going to have 1200 kg per meter square, right? So once now the system is divided into symmetrical shapes, then as a result of that what is going to happen is that it is going to be easy for us to calculate the difference that is going to be there in this what you can say the floor masses that are going to be there, right? So once system is converted into symmetrical shape, then the next step is to calculate the coordinates or center of mass. We have to calculate the center of mass in both the directions, that is x direction as well as y direction. So I will name the coordinate in x direction as xm, and I will name the coordinate in y direction as ym, right? Now how to calculate? So again it is very simple. You have to use the concept of center of gravity, where for x bar, we use the formula x bar is equal to a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. So same thing we are doing over here also, right? So if I am talking about x direction, then I have written that xm is equal to, first what I have done is the value is, that is the value of load is given to me in kg per meter square. So what I will do is that in order to convert into kg, I will multiply with the area, right? So if I look at the first part, the mass of the first part is 1400 kg per meter square. And what is the area that is going to be there? Then I can say that 10 meters into 6 meters is the area where the 1400 kg per meter square is concentrated. So I write xm is equal to 10 into 6 into 1400. So as soon as I write 10 into 6 into 1400, that means what is going to happen is that the weight is converted into kgs, right? Because I have multiplied with area, so kg per meter square will be cancelled, and we will get the value in terms of area. Next is a1 y1. So y1 is what? The coordinate, that is the CG of that particular system, right? So if I look at the figure again, then I can say that for the first part, my point A is going to be my origin point, right? So from the origin point, if I want to consider the CG of the first part in the x direction, then I can say that it is going to be located at distance 5 meters from the point A in the x direction, right? So y1 will be 5. So it is 10 into 6 into 1400 into 5. Then coming to the second part, that is A2. Again, if I look at A2, then I have converted into the second part, that is 1000 kg per meter square. So 1000 kg per meter square, so it is going to be 10 into 8 into 1000, right? Because 14 is the total dimension, 6 meter is the dimension of the first part. So 14 minus 6 will give me the value of 8. So that is why it will be 10 into 8. And second thing, again, what is going to happen is that the CG of this particular point is going to be located at 5 meters from the point of origin. So again, y2 will be 5. So same thing can be seen in that particular calculation, right? Coming to the third part, which is 1000 kg per meter square. So if I look at the third part, then 1000 kg per meter square, and what is the floor area for that particular portion? Then I have converted into symmetric shapes, right? So as a result of 20 is the width and 10 meters is the length of that particular area. So it will be 1000 into 20 into 10. And what will be my distance from the point of origin? Then it is going to be, for that particular part, the width is 20 meters in x direction, right? So the CG is going to be at 10 meters, and from 10 meters, another 10 meters is going to be the point of origin, right? So 10 plus 10 is going to be 20, right? So the point of origin, or you can say the y coordinate, that is y3, will be 20. And similarly, same thing will be for y4 also. So xm is equal to a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. And when I will be able to do this thing, then as a result of that, you can see that my xm, that is the center of mass x coordinate value, will be 14.65 meters, right? Similarly, if I look at the y coordinate, that is in the y direction, then again same thing will be there. If I look at the first part, then in this first part I can see that 1400 kg per meter square is the value, right? So 1400 into 10 into 6 will remain as it is, and I have to consider the y coordinate from the point of origin, right? So if I considering the y coordinate from the point of origin, then the y coordinate CG of the first part is going to be at 3 in y direction, because it is going to be 6 by 2, right? So it is 3, and plus the other distance from the point of origin is going to be 8. So 3 plus 8 is going to be 11, right? So as you can see, I have written the value of 11. Similarly, for the second part, again, if I go back, then in case of second part, the value is going to be of the y coordinate is going to be 4, right? Because it is going to be 8 by 2 and into area. For the third part, again, the area is going to be 10 by 2, so it is going to be 5. So that is why the y3 component is shown as 5. And for the last part, again, it is going to be 4 meter is the width in the 4 meter is the length in y direction. So 4 by 2 is going to be 2 plus 10 meters. So it is going to be 12. So y4 is going to be 12. So again, applying the formula a1 yy plus a2 y2 plus a3 y3 plus a4 y4 divided by a1 plus a2 plus a3 plus a4. So when I substitute all these values, then I will get the value of ym is equal to 7.383, right? So thus I can say that for this particular floor system, the center of mass coordinates are going to be 14.65, 7.38 meter, right? So this is how the center of mass of a particular floor can be calculated, right? I hope the example is clear to you. You can just have a look. A simple application of formula is that is x bar is equal to a1 x1 plus a2 x2 plus a3 x3 plus a3 a4 x4 divided by a1 plus a2 plus a3 plus a4. And similarly, a1 y1 plus a2 y2 plus a3 y3 plus a4 y4 divided by a1 plus a2 plus a3 plus a4. Right? So that is how x and y can be calculated. Next example, similar type of example where we are going to find two things. First is we are going to find the center of mass also. We are going to find the center of stiffness also. Right? So calculate the center of mass and center of stiffness for a one-story shear wall masonry system as shown in the plan and having a rigid diaphragm action. Right? Where four shear walls are shown with their relative rigidity or stiffness by means of S1, S2 and S3. Right? The height of the wall up to roof level is 4 meters. The height of the parapet wall above the roof level is going to be 1 meter. Self-height of the roof is 3 kilonewton per meter square and self-height of the wall is 5 kilonewton per meter square. And if I look at the plan, then it is 18 meters by 8 meters is the plan area and 4 walls are shown, that is wall 1, wall 2, wall 3 and wall 4. Right? All the 4 walls are shown. So again same thing is going to be there. First thing is I need to decide my origin point. That is why I am naming the 4 corners as A, B, C and D and taking point A, that is the leftmost bottom corner, as my point of origin. And once I have taken this particular as my point of origin, then I can start the calculation of center of mass, that is xm comma ym. So let us start. Right? So when I talk about the center of mass, then in case of center of mass I have to consider 5 elements. First is the roof itself. Second is going to be wall 1, wall 2, wall 3 and wall 4. Right? So similarly 5 elements weight I have to consider for calculation of center of mass. Weight of parapet can be neglected because it is going to lie above the floor and same time it is going to have a very negligible value as compared to that of the remaining elements. That is why the weight of the parapet is not considered in this particular calculation. Right? So if I start with the roof slab calculation, then I know that the area of roof slab is 18 meters into 8. Right? So it is going to be 18 into 8. Same times the self-height of roof is given as 3 kilonewton per meter square. So it is going to be 18 into 8 into 3. That is going to give me 432. Right? And if I calculate the distance of the floor or CG or distance of CG of the floor from the point of origin, then in the x direction it is going to be 9 because 18 meters divided by 2 is going to be 9. And in the y direction it is going to be 4 by because it is going to be 8 divided by 2, that is equal to 4 meters. Right? And then the fourth column is w into x and w into y. So that will give me the component in the x direction and the component in the y direction. Similarly, calculation of wall 1. So in case of wall, again I am given two things. First is the self-height of the wall. Second is the height of the wall. And I can calculate the length of the wall from the plan. So if I am talking about wall 1, then I can say that the self-height of the wall is given as how much? Self-height of the wall is given as 5 kilonewton per meter square. So 5 is going to be there. Height of the wall is given as 4 meters. And you can see that the length of wall 1 is 8 meters in plan. Right? So 5 into 4 into 8 is going to be the weight of wall 1. Right? So 5 into 8 into 4, that is equal to 160 is going to be my first. And second thing, if I am talking about the x and y coordinate, then in case of x coordinate the value will be 0 because it is going to coincide with the centroidal axis. And in case of y, it is going to be at 4 meters because y is equal to 8 by 2, that is equal to 4 meters. So again w into x, w into y. Similarly, we calculate for wall 2, wall 3, wall 4, do the summation of all the weights, do the summation of w into x and do the summation of w into y. And once that is done, then if I am going to apply the formula, xm is equal to sigma w into x divided by xm and sigma w into y divided by sigma m, then I am going to get the xm and yn coordinates, that are the coordinates for the center of mass. Right? So as you can see, xm is equal to sigma w into x by xm, sigma w into y by sigma m. Right? So the coordinates are 8.69 and 3.19 meters respectively in the x direction and y direction. Right? So these are the coordinates for the center of mass. So here the first part of the problem is solved, that is the calculation of center of mass. Now the new thing comes, that is the calculation of center of stiffness or center of rigidity. So let us start with that calculation as well. Again, the calculation of parapet is neglected in this particular case, right? So keep that thing in mind as well. So If I want to calculate the center of stiffness, then again I have to prepare this kind of table where wall 1, wall 2, wall 3 and wall 4, 4 walls are shown. The stiffness of these walls are shown in the figure that we have seen earlier, that is S1, S2, S3 and S4. That is, now out of this S1, S2 and S3 and S4, the walls that are going to be parallel to X will have the stiffness in X direction, and the walls that are going to be parallel to Y will have the stiffness in Y direction, that is Sy. So if I look at the figure again, then wall 1 is parallel to Y, so that is the stiffness value that is given for wall 1 will be shown as Sy. Similarly for wall 3 also it will be shown in Sy. And wall 2 and wall 4 will have the stiffness in X direction, so it will be listed under the Sx column, right? So as you can see, wall 1 Sx is 0, wall 2 is 0.85, wall 4 is again 0.15. And in case of Sy, wall 1 is 0.76 and wall 3 is 0.24. If I do the summation of sigma Sx into sigma and sigma Sy, then the value is coming as 1, right? Now next thing is, again I have to calculate the X coordinate and the Y coordinate with respect to the point of origin. So if I am talking about wall 1, then for wall 1 the value will be 0. Why? Because in both the direction it is going to coincide with the centroidal axis, and that is why it has to be taken as 0 and 0. So wall 1 is 0. Then coming to wall 2. So again in case of wall 2, if I go, then wall 2 is again going to be the wall which is going to be coinciding with the centroidal axis, and that is why it is going to have distance from the distance as 0 from the centroidal axis in X direction also, in Y direction also, and that is why it is going to be taken as 0, 0. Then we talk about wall 3. So in case of wall 3, we can see that in the X direction the wall 3 is located at 18 meters from the center of origin. That is the value in the X coordinate will be 18, and in the Y coordinate it will be 0, right? So if I go back again, then I can see that the value for wall 3, X equal to 18, Y equal to 0. And similarly if I talk about wall 4, then again it is going to be parallel to the X axis in the X direction, so X value will be 0, and in the Y direction it is going to be located at 8 meters from the point of origin, therefore Y will be equal to 8, right? So that is why the Y component will be 8. Then the fourth column is showing Sx into Y, and fifth column is showing Sy into X. And once that is done individually, then the summation of sigma Sx into Y, sigma Sy into X has to be done, and then the calculation for coordinates can be done by applying the formula Xs is equal to sigma Sy into X divided by sigma Y, and similarly for Ys is equal to sigma Sx into Y divided by sigma Sx, right? So if you apply this formula, you can see that the value of stiffness coordinates Xx is equal to 4.32 and Ys is equal to 1.2 is available, right? So I hope that the calculation of center of mass and center of stiffness is clear to you by means of the two examples that we have shown in this particular